With this over here, I will slowly go down and I will check the receive buffer. What data have we received over here? So I'll simply check before I send an acknowledgement over here. If let's say strcmp, and if we type over here, let's say for example, receive buff, the buffer that we have received, I think I will need to make it a global variable, not a global, just something that my other part of the code can read. Null semicolon, I'll specify over here as, let's say, since we already defined it, and if receive buff is equal to, let's say, sysinfo equal, let's say 0. If it is equal to sysinfo, then we'll go ahead and run the command. Else we'll simply send an invalid command over here. So I will just type this out. Receive acknowledgement. I'll just copy and paste it over here. And I will change this value, this name over here, because we already have defined it at the top over here, as can be seen here. So I will need to change this value. Let me type return buff over here. And I will maybe just write it as over here as, let's say, return buff equals to act received. Or let's say invalid command in this case, in case we have received invalid command. I will delete this portion and let me see. Car pointer return buff equals to invalid command. This is what the code is actually currently pointing out to right now. However, if we have received sysinfo command, we will type sending an acknowledge, sending response, create file, connect to the slot, connect, print connected. And before we return anything, actually I'll just copy this because this can be a global value. And perfect. So since we're going to return at least invalid command or something else, we will simply first connect. We will check if our command that we have received is sysinfo. If it's sysinfo, we will go and let's say send a response back. Else we will simply go and write that it is an invalid command. So I'll copy, paste it here. We'll also, let's say, take this, paste it over here because this is what we are going to return over here and here. So if it is not sysinfo, we'll go ahead and return an invalid command. However, if it is sysinfo, then we will run our code that we have over here. And I will just paste it over here as car, let's say, return buff equals to sysinfo. Remember that this return buff we have allocated inside this function, which means that if we will have to free it up as well. I'll type free return buff over here. And I will just type, let's say, return buff strlen return buff +1 and perfect. Which means if we have received our system info command, we'll go ahead and run that, take the output, whatever output it is there, we'll go ahead and send that across. However, if it is not this command, we'll simply go ahead and send an invalid command over here. I'll share this piece of code with all of you in a sec, provided that this works. And unless I have done some mistake over here. I started this, I will go here, I will run, let's say if I run who am I, and sorry, my bad, I think, yeah, my bad, I connected both of them on the same slot. Let me change the slot name, perfect. And my server slot, yeah, perfect over here. So you can see I'm getting an invalid command over here, which is totally fine. If I run sysinfo, for example, I should get the output. And one sec, sysinfo command received. Let me check. I think when I typed enter, I hope it. Let me just print it out. Sysinfo, sysinfo. That seems to be correct. Command received sysinfo. Well, that is interesting. Command received is actually sysinfo. So what did I miss? Sorry, I'm freeing the buffer over here. My bad. That is why it is giving me that error. I will just copy and paste this at the end before we return. My bad. Decompile, execute it again, and this time you can see it successfully ran without any issue. Both the version name. So let me just share this piece of code so that it's easier for you to get working, just in case if required. Where did I modify this code? Yeah, the same code. Okay. Let me just clean and share this code, else it will contain a lot of object files and exes, which Discord will start shouting that it's malicious. So I'll delete this. Let me see what is the size of this. 75 MB. Yeah, I think it's because of this stupid set of object files that it creates. I think I should be able to delete it safely. Ah, yes, it won't allow me to. Let me just go and do it from my Linux system, because Microsoft does not allow you to delete the VS Code file when when the Visual Studio is actively running. Let me just share it directly over here, and perfect. 4.49 kilobytes. Okay, I've shared that code over there. Yeah, I could have just copy pasted the code as well. I've shared the mail slot underscore CMD in the OTD channel. So any doubts or any questions on to this specific part, how to send and receive command or responses? Any doubts, any questions till here? Which part? Sure. Which portion, Mark? Sure. So let me explain this over here. There's not a lot of difference. When we receive the command here in our server, so basically what we are doing is on the, sorry, let me open the terminal. On the server side, we are listening, this exact same thing. On the client side, we are sending the data. If we send sysinfo, our code over here will validate whether we have received sysinfo. If it has received sysinfo, it will return the sysinfo function, get a pointer, send that data, whatever the data is inside that pointer, back to our client, else it will send an invalid command. So to explain this, you can see that we are reading, this is our server code, we are reading the data, printing this. So this is all the same. The only small part that we changed was that earlier this car receive buff was over here, because we were just allocating and erasing the data. Right now, since we are going to do a bit of a string comparison, I have moved it back over here at the top, and I have moved the free command, free basically code over here, freeing off the receive buff. And after that, once we have received the command from the client, we are going to create, again, connect to the client slot name. We're going to compare the data that we received, whether it is sysinfo. If it is sysinfo, we'll do a few things which I'll explain in a sec. If it is not sysinfo from the client, we'll simply return an invalid command over here. However, if it is sysinfo, we will run this sysinfo function, which returns a heap which contains a data. If you take a look at this sysinfo function that we have, it basically returns a pointer to a car, basically heap that we have. We're just extracting the data over here. Basically our calloc, as you can see, calloc is your similar to your malloc. It just allocates the data, zeros it out. We are copying our information that we have extracted using the RTL get version API call, copying that inside our temp buffer, finally copying inside our buff variable, which is allocated on heap. And we'll simply return the buff variable, which you can also see we are returning a car pointer. Once we receive this car pointer over here, if we have sysinfo as a valid command, we're extracting that, sending that over the mail slot, freeing it up, and finally closing the handle. Does that answer your question, Mark? Let me know if I missed something. Okay, cool. And if the answer is long, we'll have to make a while loop for. Yes, that's correct. If the output over here is pretty long, right now it's hardly a few bytes, as can be seen over here. It's basically only these many bytes of data. if this value is more than 424 bytes, then you will have to perform a loop over here to basically write the file. Sorry, over here. Just perform a while true loop and write every 424 bytes over here till there is nothing more left to send. Does that make sense? The while true loop will simply go over here. Cool. So basically, while true, read the first 424 bytes over here, send the 424 bytes. Again, go inside, read the next 424 bytes. 423, I think, because the last byte will be a null byte. That is the reason. Read the next 423 bytes using an offset, send that across, and so on. It's as simple as that. Okay. So, any questions? Anything else? Anyone wants me to explain anything else? Feel free to let me know. Any other questions or doubts? Okay, no questions, no doubts. Perfect. We can go on to the next part, that is basically process injection. Now, most of you might know what a process injection is. These are the vaguely known techniques since the early 2000s, and they were mostly used for patching a ton of information in memory. However, lately, since the past few years, more like past 2 decades, I can say, it has more often being used for malicious purposes or injecting custom code into memory, which can modify how the execution flow of the code would be. That's what process injection is, a small piece of stub or code into memory that can either download a new stage, execute that, and give you a response back, or maybe just directly a large stage, something like a reflective DLL or a C# code or a PowerShell code into memory that can execute further code. So we're going to take a look at this by taking some examples from Metasploit's code. A few things to keep in mind is that DP and ASLR, we won't be going into writing shell code or something similar in our offensive tool development workshop, because that's a part of the MOS workshop that we have. However, a few things to keep in mind over here is that whenever you create a shell code, you cannot execute the shell code unless that memory that you have allocated is executable. Prior to Windows XP Service Pack 3, I think by default the stack was easily executable. I think till SP1 or SP2, Service Pack SP1 or Service Pack SP2. The stack was by default executable. It did not have a lot of privileges and permission privileges, and you could directly execute that on stack. Microsoft later on introduced DEP, that is data execution prevention, which means you cannot execute a read-only or a read-write region. The executable region must have execute privileges in order to execute. Similar to that, we also have ASLR. Previously, most of the memory region code or the offsets were similar in all systems, because of which, if you could crack up, if you, let's say, if you find a buffer overflow or an executable region in your own system, you could exactly copy the same base address into the target system, or more like the base address and the offset into the target system, and it would run. However, that is no longer valid due to ASLR, which is your address space layout randomization, which means every time the DLL is loaded, now it won't happen every time the DLL is loaded into memory. That's wrong. The correct logic over here would be that every time the DLL is loaded into the specific system, which means whenever you reboot it, whenever you shut down, or whenever you install a new OS, the whole address space of where the DLL is loaded is would basically be different, which means it might stay the same till the system is rebooted, but once you reboot, the whole value would be different. And when I say it would be different, it simply means that if you open any debugger and you see these symbol addresses over here, cmd.exe is loaded at B0000. Now, if I kill it, run it again, and take a look at symbols, this value will be the same. Same goes for this ntdll.dll. As you can see over here, this is basically the address of ntdll, that is 770000. Similarly over here as well, and so on. But let's say you reboot the system, or you reinstall the whole OS, or you install the OS in 10 different systems, the value of these base addresses that you would see in all the 10 systems would be different. That's what we call as a address space layout randomization. These values would be different. Now, there are several other ways to bypass this as well, which is itself altogether a different, I would say more like a workshop kind of thing, because that is more towards exploit development. We, in case of building malwares or post exploitation tools, you won't have to worry about ASLR most of the time. The only thing that we have to worry about is DEP, and that too you won't have to worry about most of the time in case you're not doing any exploitation, because you can simply create an executable region in memory using virtual alloc or NT-allocate virtual memory, or change the permissions of an existing region using the virtual protect X or virtual protect or NT protect virtual memory in this case. Let's see how that can be done. We can create a executor, we can create a payload using Metasploit. This is what we will be using for our current example. A simple reverse TCP payload, which should be around 511 bytes in memory. You can execute code into memory using multiple different techniques, either by calling, once, let's say you have allocated some region in memory, copied your shell code to that region. The only way to execute that would basically be by calling, sorry, not, I won't say the only way. There are multiple actually ways to execute a specific region in memory. You can either execute it via directly by calling that memory region as a function pointer, which is what I have done over here. Or you can call it via by calling create thread or create remote thread or any other API call. Now, one thing to note here is that the best way to call a region is by direct, if you're already into memory and if you want to call another piece of region in memory, this is the best way to call it. This was not really the best way, I would say, to call it earlier, because a lot of times you can actually call a thread by using create thread or any similar API calls. But the problem over that was that in current scenario, when you're dealing with EDRs, right? EDRs use something what we call as ETW-TI. Now there is ETW which works in the user land. There is ETW-TI which works on the basis of sensors that Microsoft has installed into the operating system. There are more than, I think, around 67 or 70 sensors in total currently into every Windows operating system, irrespective of whether you install an EDR or not. And EDRs, however, in the kernel land can utilize these sensors to extract how or what piece of code is being executed into the user land. Which means the moment you call something like create thread, NT-create threadx, or any similar API call which actually executes memory, that all of those, I won't say all, but most of those can be detected by your ETW-TI, that is your event write in and threat intelligence mode, and that data TI is basically captured by your EDR such as Sentinel-1 or Endgame, and they see who executed that code. If you're calling create thread from an existing RX region that is not allocated by the user, then it will basically kill that specific thread in this instance. So however, what we can do is, instead of, we can just skip calling create thread unless until obviously you don't have an option, and we'll simply typecast whatever our executable code is to a function pointer. So in this case, what we have done is that we have allocated some region, casted it to a specific variable. Now this function variable is of data type of pointer, and since we are which basically returns void, which means it will not return anything. And since we have these parentheses, it means that this is a function and it takes any argument type that we have specified. So you can execute this function variable something by calling something like my function variable over here, whatever your my function is, or you can simply combine all of this into a one single piece of code like this. Your executable code, typecasting it to a function which returns a function pointer. So this is the this specifies that it's a function. It specifies that it doesn't accept any arguments over here, unlike this one which accepts an argument. We are not accepting any argument. We are executing this pointer as a function and it returns of the type void. And once you have typecasted it, we will simply call it by using the parenthesis. So in short, we are executing our code executable region as a function pointer. There is no detections against this because this is like any other function execution in memory, unlike create thread, which has its own set of syscalls that can be detected. So let's see how this can be done. Over here, this is a very quick example over here of create code execution. You allocate some virtual memory. If the virtual memory is valid via virtual alloc, we are executing it as a page execute read write. If it is valid, copy the executable shellcode buffer into the new region, call create thread, or maybe we will call function pointer over here and execute it. A quick example can be taken a look at by going over here, file, open project solution, OTD day1. We should have injections over here. Perfect. And let's take a look at our default injection, which should be, yeah, let me take an example of code exec ptr. Okay, I will pin this. So we have a very small piece of code. As you can see here, we allocated the virtual memory for this code. It should be 511. My bad. That's basically the size of the shell code, as can be seen here. Over here, we have called virtual alloc, returned get a got a pointer, copied our shellcode to that region, change the permission to page execute, just page execute. So it should have an X region over here into the memory. And finally, we typecasted our executable region to a function pointer and executed it over here. As simple as this. So I'll just build it over here, copy this specific region. I will just go back here and simply let's say start Metasploit, MSF console, use exploit multi-handler, set lhost, set lport, um, set, yeah, I think that should be it, right? Run, or did I miss anything? Yeah, I think I missed something. No, it should run, yeah. Sorry, my bad. I think I forgot to add the payload, set payload, yes, perfect. Run, let's run this and see what we get. Sorry, I will close this, run it over here. And you can see we have received a stage from Metapreta. Sorry, not who am I, my bad. I'm used to running that command. Let's see how this looks like in memory. File, open, day one. We have our process injection, code PTR, debug, 61 kilobyte. You can see we have tons and tons of information. For those of you who might have who have already um, accessed my Dark Vortex workshops earlier, sorry, the Malvern Struts workshops earlier, you know what I'm talking about here, the main CRT startup runtime, when you create a position independent shellcode that we have. This is the remaining portion, which is basically from your msvcrt.dlls garbage that by default is added a lot by your Visual Studio Code. However, we are going to just go to kernel 32, search for virtual alloc, add a breakpoint, run it, we hit our breakpoint. Let's take a look at the registers that we have. RCX, RDX, R8, R9, first, second, third, and fourth argument as per the Microsoft documentation. So RCX should basically be null, as we can see over here. RDX should be 511. 1FFF, if you convert this to, let's say, 1FF, you can see it's basically 511 hex to decimal. R8 should be 2000 for mem reserve, 1000 for mem commit. So 2000 odd with 1000 becomes 3000. You can see over here in the R8. And finally, we have page execute read write, which is 4, which is R9. So R6, RDX, R8, R9. After that, we'll go call virtual protect. Let me add a breakpoint here to virtual protect. Then we have virtual protect over here. R6, RDX, R8, R9 again, we should contain our function pointer. Since we've already copied our data to our new executable region, let's see what we have. So we have RCX, which should contain our shellcode region. RCX, right click, follow it in dump. We can see FC4883E4, which is exactly our shellcode FC4883E4, because we copied our shellcode to the address pointer, and this address pointer is into the RCX region, which you see over here basically. Then we have RDX, size of the address pointer, which should be 511 again. RDX. Okay, this is interesting. Yeah, by default, when I added this, it only added the size of our address pointer. So I think I should probably change this. This should not be size of actually. I know that is something that Visual Studio does. When you type size of, it basically takes the literal size of the address pointer. And since this is only LP void is basically of 8 bytes. So you just added those 8 bytes. That is not something that you should do. My bad. Reload it, run, and you can see now the RDX is 1FFF. That is basically our RDX over here. Then R8 should be 0x10 and R9 should basically be 0 again. Sorry, R9 is basically a pointer, so it will not be 0. The place where it points to should be 0. So R8, as you can see, 0x10. R9 is a pointer. If you follow this pointer in dump, it should return 0. You can see over here, dword value 4 byte, which is 0. I will click on the play button, return next, and you can see that after the virtual protect, we have our call over here. And this call region is basically to a location, and that location should be our executable memory region. So you can see that this is actually calling RBP plus pointer at the RBP plus 8 is this location, which contains 29268F00. If you follow this in dump, you should see our memory, sorry, not this, my bad, follow in dump RBP plus 8. You can see our shellcode here. If you follow this in memory map, you should see only a single permission, that is X region or E, that is execute. You can see it is basically belonging to E region, that is execute, which is what we are executing. We step into it and you can see FC4883E4, which is our shellcode over here. Does this make sense? How to trace down your shellcode and execute them? Any doubts, any questions on this specific part? Any questions? Is it too confusing? Let me know. I will explain it again. If it's not confusing, then we can proceed. Let me know how you want to proceed. Any questions, queries, anything else? No questions? Looks like everyone understood everything. Perfect. And you can also take a look at into process hacker. By the way, the process hacker should clearly state the memory region as multiple RWX regions, because normally these regions are what your Metasploit shellcode allocates for multiple different modules, which is heavily detectable. And that is the reason why it gets detected as well. Going on to the next slide deck, we have remote thread execution with the thread API, file, open, project, CRT inject. Again, the core logic stays the same here. Sorry, my bad. Virtual alloc, instead of virtual alloc, we are calling virtual alloc X, because virtual alloc X allows you to pass an extra argument, which will be a handle to a target process. So basically, either if the user supplies an argument, open a handle to that process by extracting it by you taking the PID from the argument, converting that PID from string to your integer, opening a handle and copying that handle to H process. If the user has not supplied anything, create a new process called as notepad.exe. You will by default get the handle inside your process information structures H process variable. Allocate memory over there, write process memory, protect the memory with execute permission, call create remote thread over there and wait for it to complete. As simple as this, nothing fancy. Let's see how this works. Over here, let me go back and run this again. And paste, run, and we should have a region. As you can see, this should be from our notepad that we have created. You can see the notepad. Let's see, we have a few threads. Does this seem interesting? 0x00. This is basically a proof that your shellcode is running in memory and it is not a legitimate region. The moment you see something like this over here, and you will see this for almost everything, including Cobalt Strike and not just Metapreter, because the moment you execute a thread which is not belonging to somewhere on disk, you would see something like this. And this is the best way to identify that a shellcode is running into memory. Legitimate regions will always be backed by base thread init thunk, and RTL user thread init thunk, until unless you modify or spoof the stack, which is what something that we do in our MOS workshop as well. And in case of memory region, you should have multiple memory regions over here. As you can see, multiple RX, three RX regions and one RWX. So it looks like Metasploit did change their code in the end from multiple RWX to multiple RX, but it is still as bad because you can see that it still has the MZ header over here. What you can simply do is, let's see, we have this RX region, another RX region, another RX region. So let's say right click and let's save this memory region to desktop. Let's save it as, let's say, msf.dll. I'll go over here, file, open. Let's go to desktop and let's search for msf.dll. And you can see that this is actually a DLL itself, the injected region, which means Metasploit also injects RWX region. Page execute is not flagged. Instead, yeah, both of them gets flagged. Page execute as well as page execute read. I would not recommend having any of them into your region. The only reason I am, and one more thing to remember is that page execute read only and only works for position independent shellcode. If you are going to execute a reflective DLL into memory, that will not work with page execute read, because for reflective DLL to work like Cobalt Strike, you will need a read region because it reallocates its own region into memory. The reason why ours work, because this small piece of code is purely position independent that we have, which means you can just copy it to execute read because it is not going to read itself again. It is only going to continuously execute a stream of opcodes into memory. Unless in case of if you're going to pass it for a reflective DLL, that won't work because it reads itself, reallocates itself into memory somewhere, similar to what your Cobalt Strike or your Metasploit shellcode does. Only pure position independent shellcode stage basically does. Okay, so going back over here, this is something similar to what I can say for your one of my brute retels code. You have a stageless code and a staged code. In case of stageless code, which is of around 200 or 300 kilobytes, you cannot call it with page execute read permissions. I think you can actually call it in case of brute retel. My bad. Yes, you can call it. However, there is also 7 kilobyte stager, which basically is something like this, which you can call it without without read privileges as well. And you can see over here the dump file that we extracted, this RWX region which we dumped. This is nothing but your P header itself, which is nothing but your DLL of Metasploit itself. The text section over here, the MZ header, read only dot data. You can see the export directory, which is reflective DLL itself. The moment you see an export, the moment you see an RWX region into memory, right click and dump it. And if you see an export directory, it means it is a DLL into memory. Your import directory, you can see that ws2_32, which it uses to create a reverse socket connection. Crypt32 maybe for, I believe, encrypt and decrypting some certificates over here. Win9 for HTTPS connections and a lot of other information over here. So is this clear how this works? Memory region and memory dumping and shellcode execution. Any doubts on this specific part? My bad. My throat is fully dried up. So no questions over here, no doubts. Okay. Cool. This is the CRT. Yeah. Now this is a bit more interesting, callbacks, which is what I like to use a lot actually. Let me kill this and let's try to understand what callbacks actually are before we get into that. Now, unlike your shellcode region, which gets executed directly, callbacks are as simple as it sounds. It calls back to an alternate function. That's as simple as it can get. So you can basically call a callback as a call after, which means it refers another executable region into memory or an executable code where it passes the current context to a different region. So instead of going into this theory, you can actually read this if you require. let me explain this in a more logical concept by directly going into a sample piece of code. Let's say you have an int main region over here. You have a car value and a float value over here, right? And then we have a function. Now this function is a function which performs the callback function. So what we are doing over here is that we call function which calls back with a, b, and our third value that we have. In our function which callbacks, you can see that we are taking three values: arg1 car value, arg2 float value, arg3 is a pointer to a function over here. And finally, whatever the user provides, irrespective of what this function is, it will go and execute that function, which means this is a callback which calls back to your custom function. So when function which calls back executes user provided function, that is this, it will call back to this function, that is my custom function, which is this, which means you are not directly calling this function, you are asking some other region into memory to call your shellcode. This is pretty good in terms of evasion as well, unlike calling create thread or create remote thread, because if your create thread and create remote thread is hooked, any EDR can check the registers and check which region is actually calling up. Unlike in case of this callback region, where you are actually calling a legitimate code within NTDLL or kernel 32 or any other DLL, and that piece of code, the legitimate region which belongs to disk, that may or may not be hooked. Most of the time it might not be hooked, because there are like from what I recall, there are more than 60 or 70 such callbacks, and probably more which I might not know of, some of which I have already added into the code repository that you got over here. So there are a lot of callback functions which, and ADRs cannot hook all of these callback functions. So basically you can just ask your callback function to call your executable region, which means it will look like a legitimate region in memory is calling a shellcode, which might look like it is totally legitimate, because Windows by default does that as well with C# based codes over there. So in this case, this is what your callback looks like. Is the callback logic clear over here, how a callback works? Any doubts on this part? On the callback part, because we'll be utilizing a few callbacks to see how our shellcode logic looks like into memory. Okay. So let's go and take a look at how callbacks actually work. So I think I have provided, I don't know, we should have a few set of samples here. Process injection, and yes, yeah, we have a lot of samples. Obviously I cannot go through all of these samples, so I will just go through a few of them. Let me search for we have set timer. Yeah, let's take it. We have set timer, create fiber, or let's take a very let me just open these up, and I'm basically selecting one which is a bit more complicated. I'm just trying to think which one is it. Let me take an example of this set timer itself. So you can see what it does over here is that it calls virtual alloc on this shellcode. Basically this size of the shellcode, allocates that region, copy your shellcode to the allocated region. After that, let's see what set timer function is actually supposed to do. So let's see, the first argument it takes is basically a handle. Second argument it takes is an ID over here, a handle to a window. In our case, what we are doing here is we are we're passing null as a handle. And the second value that it requires is a pointer to an ID, a non-zero timer pointer. Over here, in this case, we are going to supply it as dummy, any value that is required. It states that over here that it should not be zero by default, a non-zero timer, but it won't really matter to us because we're not going to actually utilize this function. We are just going to use it for our malicious part. An unsigned integer value with the third argument over here, the timeout in milliseconds after which this code will execute. We're going to supply this as null, which means it will execute instantaneously. And finally, a timer proc, a timer procedure, which will execute after this timer expires that you have specified. So after this seconds expire, which is 0, it will execute whatever function value that you specify, which means that our set timer will actually go and call this specific function that we have. Finally, we'll go ahead and call. So now this won't execute until we call get message or something similar, and we'll print this value that we have to screen. We should also be actually able to just call something like maybe wait for single object with -1 and -1 over here. I'll execute this. I'll just Control A, Control C. I will open up a new project over here. Let's say a console application, C++ project. I will set the path over here to day1. Let's say I'll just post it over here. I'll select this folder. Timer exec, location timer exec, create, and yeah, Control A, Control C. I'll rename it to C instead of CPP, not a CPP fan. And let's say return 0 after a semicolon here. Compile it to x64, build. It succeeded. Let's execute this code that we have over here, and I will also start up run a listener here. Let's run this. Let me see. Oh, I think we need the get message W to instantiate this timer. From what I recall, give me a sec. I think that is what we will require. My bad. Let me run this again. Yeah, that is required to instantiate the actual code. Because when you call, let's say this timer is supposed to read information from whatever message pointer, whatever message box you pass across. Since we have supplied it as null, it will take the handle of the current process. Sorry, this is basically the code over here. And when you call get message W, it will instantiate whatever timer has basically been allocated over here. This should be defined over here as well. Somewhere over here, which I did read. Okay, I'll have to scroll through this code. You can read up this documentation over here, not a problem. But normally what's happening over here is that the moment you call get message W and dispatch message W, it will instantiate your timer callback and execute this piece of code, which is what gives you this shellcode that you have over here. So basically there are actually a lot of code over here, and you can go through these samples over here. Windows does a really ton of stupid things to execute basically pieces of, to execute callbacks into memory. You can also execute, let's say, for example, there was a certificate based one as well, which I cannot find right now. There's actually a, I think alternate shellcode exec. I think that was the name of the repository. GitHub, I think. I don't recall the name. Maybe someone has it. Yeah, I think it was this one. You can just go through this. I can see it's copy file, cert enum store, and create thread pool wait. There are tons and tons of other ways how you can execute callbacks. So any questions or doubts on callback based execution? Any doubts, any questions on how callbacks work? No doubts, no questions, or a lot of doubts and a lot of questions? It's either or. Okay, looks like, do you put callback for remote process? That is a really good question. You can do that, but that would require a bit of thread hijacking in order for callback to work. I will explain that in a sec, how you can use callback, for example, something like this, alongside thread hijacking to actually execute your code. I'll come back into a bit because we do have that in our workshop. But apart from that, any other doubts still here? Okay, let's go back to our slide deck and see what is next. APCs, asynchronous procedure calls. Asynchronous procedure calls are those which work alongside your existing thread. It needs the thread to be in an alertable state, which means your thread should be in a suspended state, or it should be waiting for something else to be complete, so that it's in a paused state using either sleepx or maybe something like wait for single object, or it is waiting for something else. In short, as simple as that. So what happens over here in terms of QAPC is that you take a thread which is a suspended state, you tell the thread, or more likely the kernel, that I'm queuing a specific asynchronous procedure call which should run first before the thread actually runs. So when you resume the thread, your callback, or not the callback, sorry, your code or your asynchronous procedure call that you have, which you have queued to the thread, that will run. And once that function is complete, the main thread will continue to execute. So over here, that's what we are going to do. We are going to create a process in a suspended state and queue our code onto that. So file open, process injection, we have APC inject. Again, we are creating a notepad process, allocating some memory, and you can see that we are creating this process in a suspended state here, writing our code into the target process, queuing the APC call here and resuming the thread finally. You can see the queue APC call over here is this. Any guesses why this value is null or what this value might be? This is a thread in which you are going to queue APC. Any guesses what we can pass along over here? It states long PTR, but any guesses what we can use this third argument for? Exactly, for parameter. If your shell code accepts any kind of parameter, you can pass that across, which means if you're going to execute a reflective DLL, you can pass a parameter to the reflective DLL over here. Build, and it is complete. Copy, exit, run, go back and run this. And finally, we have a state, and this should be from our get PID 4908. Let's see, we have 4908 as notepad, and our code should be up and running. Let's see how it looks like in the threads part. Do you guys see anything interesting here, unlike the previous examples? All of these are RTL user thread start, apart from the main one. Any guesses why? Why the main thread is not backed by anything but other threads? Any guesses? Everything is backed by a region except something over here that looks totally weird. Legitimate threads should look something like this, but not the main thread. Any guesses why? This is basically a way to identify QAPC calls. And any guess, anyone? Exactly. When you create a suspended process, you are actually creating a thread, but you're not allowing it to execute. Which means before the main thread even starts to execute, when you call create process, you are basically queuing your own call. Now, this won't happen if your main thread was already running. If you're suspending an existing thread into a target process, then queuing your call and then allowing it to continue, you won't see this because the thread would have already been started. But in our case, since we created in a suspended mode already, our thread did not even get time to start. Since our thread did not even get a time to start, and we queued our call before it, our call executed first before the thread could resume. Which means what you see over here is basically the call in this specific case, your shell code. And you can see WS2 underscore 32 because your Windows sockets was called to create a connection back over TCP to your code. And this is how we can identify whether a thread is malicious or not. So even if it is still backed by a region, you can still see the shell code pieces of code that were put by shell code onto the stack to identify it as suspicious in this specific case. So this is a very easy way to identify whether there is something malicious or not whenever you're doing any kind of thread hunting. Any doubts on the QA APC part and how this works? Yes, instead of resume thread, you can not only use NT alert resume thread, you can also call, I think it was test alert or something like that. I don't recall. I think it was test alert, right? It was test alert, yes. Let me search test alert. Test alert. Not test alert. I think it was, yeah, it was test alert API itself, I think. NT test alert, my bad. NT test alert. Perfect. Let me zoom in. As you can see over here, once you have queued it, we have NT callback return as well. I should probably take a look at this later on. I just saw that right now. My bad. Let me, yeah. As you can see here, you can use entity seller to empty APC queue for the current thread. In order to empty the queue, it will synchronize whatever APC calls are there and it will ask it to continue before it actually does anything. So you can also use this apart from NT alert resume thread to continue your thread from running. There should be more other options over here as well. This also looks pretty interesting, but yes. And I think even NT continue allows you to run, from what I recall. NT continue should also allow you to run, if I'm not wrong. Sorry, yeah. NT continue can also, it does not allow you to queue APC, but whatever thread context you have, yeah, we'll come to this part later on when we talk about thread hijacking. Basically a custom thread context and allow that thread context to run. But yeah, we'll come on to this part later on. So any questions or doubt till over here, what we have done? Any questions, any doubts? No questions? Cool. So let's go back to the next part, that is injection with memory mapped files. Now, similar to allocating a region into your own memory and executing it, you can allocate some section into a globally mapped memory, copy your shellcode over there, map that region into your own memory and copy whatever data you require, but map it to your own process as RW. Map the same thing into the target process as an RX region, only read execute. And whatever you're copying into your current process's mapped region will also look the same into the target process because that is a global section that you have created with NT create section. So basically create a section global object, copy your data to the global object by mapping that global object into your process as RW. Map the same global object into the target process as RX. Call RTL create user thread, NT create thread, or anything that you require onto the target process to ask it to continue. So file, open project solution, map view inject. And you can see over here, we have a very small piece of code. Creates a section, handle, returns you a handle to the newly created section. We'll create a global object as execute read write. Map that section, handle, to our current process. -1 basically means current process handle. We are mapping it as read write. Opening a handle to a target process, mapping it into the target process as read execute. Copy the shell code to our local section. As soon as you copy it, it should reflect the same into the target process, which is under read execute. Finally, call create thread or RT8 create user thread onto the target region from where our section of our shellcode actually lies in memory. It's as simple as that, nothing fancy here. Copy, Go back here and here. Run. Interesting. Let me see. Does it take? Yeah, it takes a PID in which it wants to inject. My bad. So let me create a notepad 9884 9884, and you can see we have received a stage over here. It should have 9884. Perfect, as you can see. It's a pretty simple thing, nothing fancy over here. Any doubts on this specific part? Creating injected memory mapped regions? Any questions, any doubts on this? No questions? Okay. Finally, we go back to the last part, that is instruction pointer or thread hijacking. So since this is the last slide for today, let me just go back directly into the code and open that up. Let's see, thread hijacking. So let's see what we have over here. We take a handle of load library A. We try to find out the address of load library A into our current process. This will be the exact same into the target process as well. We open the handle to the target process, allocate some memory into the target process, copy our shell code to the target process into the new region that we have, and change the permission to read and execute. However, we will call RTL create user thread on load library, and we will specify, as you can see over here, the third argument over here is create suspended. We are asking to create this thread in a suspended state. Once we create that, we will not supply any arguments. So when anyone takes a look at it, any EDR, it will look like a thread is created from one process to another, and that is basically in a suspended state. Now, what we are doing here is that we are going to create a context structure. This context structure contains all your registers, as you can see. Our aim over here is to modify the entry point of our thread. So if we modify the end, since this our thread is in a suspended state, it is not running. We are going to modify its entry point that we have over here with our custom entry point of our shell code. Once we copy that and let it continue, it will execute our code that we have. Our instruction pointer is going to be into our RIP where it currently resides. So as you can see, we are going to call get thread context. Make sure that you have enabled this over here. If you're going to modify the instruction pointer, that is RIP, you need context control since you're only going to modify the RIP instruction pointer. If it is context full, then you can also modify the RCX as well. You can modify RCX is going to be a thread entry point. RIP is going to be where your current thread lies into memory. This might not always be successful and it can lead to a crash if your RSP is pointing to a sensitive region. It is always recommended to use RCX, that is the reason. But you can use either of these in this case. I'm going to show you the sensitive version over here. However, you can uncomment this this part over here, my bad, this part and this part, and you can comment out this part and this part over here in order to check. We're getting the context of our thread that we created, all the registers, going to modify the entry point of the registers with our custom code that we have, set the updated context which contains the updated register code, and finally call resume handle over here. And finally wait for single object for it to wait. Let's see how it looks like over here. And before I execute this, since we are going to do it into a target process, let me add a simple, before I actually resume it, let me call get char over here and I'll type printf, hit enter to continue. When we hit enter, it will continue to execute over here. So compile it, go back, exit, run. We will take this path, which is over here. Control A, Control C. We have to specify process name. Let's say I'll start Notepad. PID is 9744. So I'll type 9744. However, I will go and attach myself to the Notepad process so that I can uh, see what is exactly happening. You can see there are several threads here. And what I'm going to do is, before I actually execute this, let me go back and see if I can print the thread handle over here. So I'm going to specify, let's say, printf thread handle colon percentage x slash n, and we're going to print the thread handle just before we continue to do everything else over here, so that we can track it back into the target process. You can see our thread handle is C0, and everything else has been done, including setting the context. Let's go back and let me do one thing instead of doing something like this, and let me do it again. Let me just reload, run. The PID is 320, and let me show you how it looks like before and after the thread context change. I will build it again. Okay, so I will go back here, and the PID is 320, as you can see here. 320, hit enter. Our thread is created. Let's go here and search for our handles. Click refresh, C0, and you can see we have our thread which is waiting. Sorry, not this one. Oh, sorry, it's a 30. Sorry, it's BC, my bad. C0 was for the previous thread. You can see we have events over here. Interesting. Thread handle BC. This should be our thread. Let me see. Interesting. Let me see what other threads are currently over here. I wanted to see the PID of the thread, which I am not able to see right now. Let's go back and do one thing. Since virtual protect RTL create user thread, so this should be the entry point for our thread since we have not hit enter over here. So let's see. Let's go back to the threads entry point and see combase TP worker thread combase TP worker. So it looks like our thread is currently not running. If you go to thread entry, this is somewhere else. Our thread is currently not started, I think. It will only start when we actually continue to run it. Go to thread entry. Yes, all of these threads are basically running, which means our thread is not yet actually created. If I hit enter, so now the instruction pointer has been changed, which is not yet updated over here. So let me go to memory map and let me search for an ER region. We have our ER regions over here. And let's see which region is. So you can see these are image mapped. This one, as you can see, this is a bit suspicious. It was earlier RW, as you can see over initial, and now it is ER. It's a privately mapped region and it is not backed by anything. So most likely this should be our region. And you can see this is where our shellcode lies. So if I hit enter over here, I should hit the breakpoint here. Enter, and you can see we have hit our breakpoint. And we should get a connection back if I let it to continue. As you can see, we have a shellback. So does this make sense? How thread injection works along with thread hijacking? Now coming back to the Alex's question over here earlier about callbacks, think of it in this way. Similar to load library, you can try to find any other callback function over here and try to use it to actually call whatever code you want to run. Not just load library, literally anything else that you require, including callbacks as well. And similar to executing callback, you can actually take the context. You can specify maybe something like set timer over here, change the context of the timers over here using your own custom techniques. So that way you will be able to perform thread execution as well. Any doubts, any queries on whatever we have done till here? Because I think that brings us back to the end of the day one's slide deck. Any questions, any doubts? Okay, there's a lot of silence in the room. Either everyone understood everything or no one understood anything. Okay, given how we can spot many of the anomaly techniques, anomalies the techniques generate, is any of the stuff OPSEC safe against a decent EDR? That is a pretty good question. So now, first of all, depends upon which EDR we are talking about. Uh, Depending upon, so every EDR has different detection techniques, right? If you're dealing with something really not so good, I won't say shit, that would not be the correct word to express my feelings. If you are talking about EDRs, like for example, Sophos or McAfee and everything, you won't have to worry about most of them. And some of these, including some basic techniques like virtual alloc and virtual exec, do work flawlessly with them. Yes, if you're talking about ATP, Sentinel-1, CrowdStrike, or as a matter of fact, even Endgame or your Elastic EDR or Silence, things change altogether with these EDR. Even one of the best EDRs that I have seen, which I haven't seen a lot of people using it, is 40 EDR. If you're ever against 40 EDR, then you should probably stop the engagement, because it is one of the most hardcore EDRs that I have seen. It's not too popular because even though it does detect a lot of things, it still has its own set of issues with the detections against PowerShell and stuff, but it does detect injections against reflective DLL shellcode very well. And the reason for that is because these EDRs do not just detect the injection techniques. 40 EDR by Fortinet, FORTI EDR by Fortinet. So now coming back to your question, so I'll answer it partly whether these injection techniques work and whether they do not. So the answer is yes and no. Cortex EDR, it basically for me it falls in the same line as that of Sophos EDR. Uh, with just a little bit tweaking, Cortex does not detect virtual alloc or virtual alloc X or something else as well. So I won't really consider it in high regard. Probably some of the best EDRs that I have seen are basically, let's say, CrowdStrike is good. It has a really good machine learning algorithm, and most of its detections are on cloud. And I'm saying that is because I have worked with CrowdStrike for more than a year, where I built detections, and I have seen its ML algorithm really picking up on signatures. But again, it's again signatures, but it does pick up on that. Then we have Sentinel-1, 40 EDR, and Elastic EDR and ATP, which heavily rely on ETW TI, the TI from kernel mode. So it doesn't matter whether you're calling indirect syscall. It doesn't matter whether you're calling direct syscall, indirect syscall, or whatever. It will detect, I won't say detect, it will catch the telemetry of a syscall being executed, like Elastic EDR, right? Correct. All of these four EDRs, even CrowdStrike has started doing that lately. It's not as good as Elastic, but it does that. But yes, these four EDRs, Elastic, 40, Sentinel-1, and ATP, all of these use ETWTI to capture the telemetry. And once they have captured the telemetry, they will try to build detections on the basis of telemetry that you have captured. Which means, coming back to the question, does this get detected? By default, if you just go and use this as is, it will kill you the instant you go and do something like this. But is there a way to avoid it? That is a correct question. And the answer is yes. There are a lot of ways that you can avoid these detections. And it's not just one single thing. You have to do a ton of things to modify to basically make it workable. For example, the first and the foremost thing is that to make sure that your initial execution does not come from a region which you have allocated, like an RX region. So use module stomping in this case. Just load up a DLL, stomp that module with your own current region, and call your thread from over there. But let's say you're using some really good command and control centers, right? I won't say really good, I would say paid command and control centers. Like for example, Cobalt Strike, or you have, let's say, Brute Turtle in that case. I won't even talk about Metasploit or any other open source C2s, because if you're in an actually really good red team engagement, you would get caught the moment you use any open source C2s. But there's also caveat to using paid tools over here. When you use something like, let's say, Cobalt Strike or Brute Turtle, both of them. In case of Cobalt Strike, what happens is that you execute a shellcode. That shellcode will bootstrap a reflective DLL. That reflective DLL will reallocate itself into memory and execute that. Which means there are three memory allocations that are currently happening. The first memory allocation will be the one which you do. Let's say you stomp a DLL and execute your code over there. But that code will reallocate itself to another code, and that reallocated code will basically go and reallocate itself again to another code, because your shell code executes a reflective DLL which reallocates itself to another region. So the remaining two regions will still get detected by your any of the EDRs you use. In case of Brute Turtle, it's also a slightly bit similar, because when you execute a shellcode, it does not contain reflective DLL, but it does contain a stage which gets executed, which means even if you back it by a DLL, there will be secondary allocation which will get detected when you deal it with something like Elasticsearch, for example. Not with ATP. ATP, I have not seen it detecting that. But coming back to the question, if you write something of your own, which does not do multiple memory allocations, and if all of them are backed by a legitimate DLL in memory, and if you spoof the call stack for every thread that you are creating, and if you try to hide your, again, comes back to the call stack again, then you would not be detected in that case, which is something which I have been doing myself with the Brute Retail. That's my own command and control center. Earlier, there were three allocations, which I came back to two. And I did find a technique just few hours before today. So today, when I was just doing some of my research before I started this workshop, and around 1 or 2 hours back, I came across a technique with the help of which I won't have to do a single memory allocation at all for any type of execution. Which means there won't be any type of detection in that specific case, which you will see in probably in a week or two. I'll release a blog on that. But yes, so can you still use these techniques? Yes, but you will have to tweak a lot of places to get it to work. Use rob gadgets, use call stack spoofing, use let's say indirect callback functions. Callback functions are one of my favorite, because there are so many different types of callback functions that even TI cannot hook them. Because in order for TI to work, or when I say TI, it means ETWTI, the one that works in kernel mode. In order for that to work, they need to know which telemetry to look at. If you use the same injection techniques, yes, that will get detected. If you use callbacks, they will be totally blind to what you are doing in this specific case. Because if they don't know which callback to hunt, they cannot even use that telemetry against it, because they will not have that telemetry altogether. But yes, so it will never be a yes and no answer. There is always a detection. There is always a way to evade it. Depends upon how deep you actually dig the tunnel and try to find out what exactly is happening. So that was a large rant, but I hope that makes sense. Exactly. That no, it's actually both. The telemetry is around syscalls actually, and not necessarily execution or allocation. The moment you call, let's say, a syscall, let's say for example you call a create thread, or you call, let's say, virtual protect or virtual lock, right? Virtual lock is, even though it is hooked, it is not that often that it is detected, because most of the people, because a lot of Windows processes by default call virtual lock a lot, virtual lock and anti allocate virtual memory. So if you directly call page execute read write, obviously you would get detected. If you do page read write, you won't get detected. If you change it to page execute read, that also won't get detected if you do indirect syscalls, and if you because that is not that often detected. But the moment you execute it, if you execute it as a function pointer, it won't get detected. If you execute it as a callback, it won't get detected, depending upon that if that callback is not hooked. But if you execute it via anything else like create thread, create remote thread, that is bound to get detected, especially when you're dealing with ETWTI. Not with anything else. Anything that does not do TI hooks, everything can be evaded with your indirect syscalls apart from that. But for ETWTI, you specifically need to hide yourself from telemetry either by spoofing the call stack or using rob gadgets or by using callbacks or by backing yourself with a DLL module in this case. Does that answer your question, Tudor? It's a lot of stuff. Building a payload or a tool. I mean, the best way I think to avoid anything is to write everything custom. The more custom tools or C2 you write, even though I myself sell, I have a product Root Vettel which I sell, I would still recommend people to learn how to build C2s and write their own, because sooner or later there is going to be a time where the EDRs will start detecting a lot of stuff. It's just going to get more and more, I would say, hard to evade EDRs. It won't be impossible because there's always going to be a way to avoid it. There will always be some new research by someone who's really good, and you will always find a way to evade most of the things. But at the same time, if you don't want too many generic detections, if you don't want to be limited by a tool, it's always better to write your own C2. It might take up time, yes, but it's always going to help. Yes, you will still be able to bypass. That's exactly correct what Fawaz said. You will be able to bypass most of the stuff, but there's also a limitation to writing your own stuff. The more features and techniques that the if you want, let's say, okay, let me rephrase it in this way. When you start building your own stuff, you realize that there is a lot of things that you will need, which is not exactly something that you might be able to write, considering you also have a job to do. At the same time, you also have to add features against it. For example, let's say, yeah, sleep does work between the main function to fool the telemetry, but not always. Even sleep gets rejected these days. Wait for single object or maybe NT delay execution are the ways to go. Those are better ABI calls as compared to sleep, because sleep doesn't get called very often. Coming back to Fawaz's answer, oh, I have to test Elastic. I got a hold of Elastic today morning, so I still have to do a few tests against it. But if it detects, then it's going to be pretty fun in that case. Coming back to Fawaz's answer, yes, when you start writing your own tools, there will be a lot of limitations. Like you have to learn how to write COF files, how to load RDLLs, how to load other process injection techniques, and a lot of things which might not be directly present. You might take up 2, 3, 4 years for you to write all those functionalities which work really well during an engagement. So it's not a correct answer to say you can write everything on your own, or a correct answer to say use everything paid. It's a lot of mixed answers if you ask me. Exactly what you said, Tudor. Unless until you have an EDR to bypass. I mean, if you take a look at my VMs over here, you will see almost all the top tier EDRs that you have over here. This is my ATP, this is Sophos, Elastic, Sentinel-1, CrowdStrike, and Cortex. I basically have some really loving customers who give access to me for all these EDRs, and I test my products over there. It's really fun when you start reversing this stuff, and how to evade and bypass most of them. There's a lot of techniques, and every EDR, you cannot write a single technique which can evade every other EDR. It's going to be very complicated to do something like that. Because if you write one evasion technique, there might be another EDR which detects that, and that will always be the case. You cannot always avoid everything. I mean, that's a realistic scenario. But you can always try to keep more and researching more and more and more and keep on doing that. VH is not currently covered as a part of that. But if you want, on the day 4 post the workshop completes, I can show you a demo of VH. I have a working code for VH and how that works. VH is a bit more complicated to understand. That is the only reason. It might be a bit complicated for everyone to understand unless until you understand exceptions very well. But I will try to do my best on day 4 if required, and I can cover that part. So I have a working code for that. Let's buy all EDRs and reverse them. That's a good question. Good answer, by the way. But the thing is, you should get access to all the EDRs. Not all EDRs sell it. I'm lucky to have a few customers who provide access to me for reversing them. And for obvious reasons, I cannot expose all the ways to evade them, because that would also be pretty bad for the EDRs, because from what I know, the EDR companies themselves do a lot of hard work behind building that. So it goes both ways. But yes, that's a few cents from my end. How do you find Defender ATP? That's a pretty good question. I have a very close friend of mine who works as a threat hunter for Microsoft. He was with me in Mandiant as well, and he keeps giving me access to everything. And he's basically a threat hunter. So whatever I do, he can take a look at whatever I am executing directly from his console. So he keeps providing me information on how to what got detected and what not, and that's how I try to evade the ATP. With ATP, it's all about ETWTI. Uh, what's not good? The telemetry. Okay, cool. I think just give me around this week. I should have a new release. No, not really a problem, because the friend that I have, he is what I can say as a bit partial, so he doesn't specifically write detections for brute retail. So yeah, that's all I can say. So he basically just lets the detections from brute retail, or basically any telemetry from brute retail, just slide. So that's one good thing about having a friend in Microsoft, or basically any other EDR organizations. But yes, that's all I can say without compromising his career. So yes, any other questions, queries, or anything else apart from whatever we have done till now, or anything else that we have done till now? I will cover the VH part for us on day 4. Just remind me on that. I sometimes tend to forget because of the number of things that I'm trying to do alone. So do remind me on day 4, and I will cover the VH part. I do have a working code for that. Cool. In case you have anything else apart from what I'm covering over here, feel free to create a list, and I will go through all of them on day 4. Cool, sure. VH is a very complicated beast on its own to get it to work. I think let me just actually share a piece of link that I have. Uh, so this VH, so VH is not actually something new. A lot of gaming communities have actually been using it since ages, I think. Let me just search. I think I had it somewhere in my bookmark. Just give me a sec. Let me search. The vectored exception handler. Let me search for unknown cheats. One sec. Vectored exception handler, unknown cheats. I think the website name is unknowncheats.org. I cannot find it on the top of my head. I think this, yeah, no, not this one. I obviously extracted some portion. I was heavily inspired by some of the posts from Unknown Cheats. It's basically my go-to when I can't write shit on my own. Yeah, I think it was this one. Yes. Yes, that is correct. So what is the issue? I think the unknown cheats link that I just posted, that should give you an idea how to catch page guard exceptions. Because I know that Sentinel-1 adds page guard to your PEB. So all you have to do is use the try to find a way to using the original base technique from PEB to find the NTDLL. Once you find the NTDLL's region, you don't even need that. You can just because NTDLL is the only region where I think it adds page guard, not to kernel 32, and add vectored exception handler API call resides in kernel 32. So extract the address for add vectored exception handler, add your own vectored exception for the region of NTDLL.dll, and try to access NTDLL from PEB. It will raise an exception for page guard, but instead of passing on that exception to the Sentinel-1's hook, it will eventually pass it to you because you added that vectored exception handler. That allows you access to the full control of how the page guard would do, and then from there on you can add more page guards to make sure that the original page guard never gets hit, or just extract whatever function pointers you require. You should not stop the execution. Whenever you don't need to stop the execution of the. You will have to keep the add vector exception handler on a continuous basis. This is something similar to what your Nighthawk claims to do about hardware hooks. Hardware hooks are done with the help of add vectored exception handler API call itself. It's nothing fancy. I think the link that I shared just should help you out with all of those with hardware based exceptions as well as your this. I would just say just extract the NTDLL, restore the page guard and continue to work because I have seen detections against adding hardware hooks. If you just read that blog, right, you will get to know unknown cheats is probably the god mode for every possible evasion technique. Even it's much better than any EDRs that I have seen working, and they probably have evasions for everything. So I would recommend unknown cheats. There is OSR online. There is rohitab.com. So these are few websites which I continuously scrape to find evasions. But yes, that's all from my end for today. We have also reached the end of, I think, our session for today. So it's 9 p.m. almost at my place. So sure, no, not a problem. If you have any doubts, I'm more than happy to answer your queries. I'll see you guys tomorrow at the same time then. And if you have any questions, bring it up tomorrow and I will see you guys tomorrow then. Cheers guys. Have a nice day and bye.